Thanks a lot to all of you for giving me an opportunity to give a presentation here. I thank in particular Manjari Bakshi, who gave me this 1 month visit here to talk to his groups about pulsars, and they're really doing some good work up here. So last few years I've been trying to do a few things on my whole life. I've been doing the strange stars and all. Then I looked at the GR solutions. At certain point of my time, I was also doing the modified gravity applied to the pulsars and the neutron stars. But basically, all of these things were tied to the neutron stars. Then of late, I moved on to looking at the emission of the pulsars, because that is one thing which connects the object up there to what we actually measure. And there has been a lot of new results from the observations which motivated me to look back to what is happening at the surface of the neutron stars or the pulsars, more so from the polar caps, where the beams are they have the seeding in energy from the surface of the star at the polar caps. So this work is mostly done with my former PhD student who got her degree in this year, Kathleen Selig. Okay, so yeah, it's good to read from here. So the basic dynamics of a radio pulsar says that the magnetic field plays a big role in a neutron star, because all of the emissions that they eject, like which goes along a distance of a few kiloparsec to the maximum, I think it has an optical depth of 10 kiloparsec. So to throw matter to such a distance, one needs to have a very strong magnetic field at the surface of the star. So then, if you think of a dipolar magnetic field, because the beams come out in poles, so a natural choice for the magnetic field structure is to have a single dipole, and then the beams are ejected from both sides of the poles. So one of them which cuts the Earth. So we do measure them, and we make our models based on. Now, when we think of dipolar structure, then we will have areas which call the closed field lines, and then we'll have the areas which are called the open field lines. The closed field lines are the areas where it is charge saturated, because the strong magnetic field leads to pair creation, and then it fills up the whole space with charge density. The density is called the Golding-Julian charge density. And the open field lines are the one. Okay, to say it in this way, that the closed field lines has a boundary with the open field lines, where it is called the light cylinder, because a charged particle going along the field lines will go at the speed of light, but then the pulsar rotates. So at some point, the linear velocity of the pulsar of the charged particle is the same as the speed of light. So the charged particle is not bound to go along the field lines, and then it will become free. So it's free to choose any path. So that maybe I should go to the next picture and tell you. So this is what it looks like. So these are the closed field lines, and these places are called the open field lines because the linear velocity here is the speed of light, and hence the charged particles are not bound to travel along the field lines. So then what happens is that here at this surface right here, when the charged particles form, they lead to curvature radiation, which comes up to a point called the inner gap region. They are accelerated up there, where they form something called, so this leads to some coherent radiation, and that one forms the beam which shoots up a few kiloparsecs. So not all of the charged particles that form here do take part in forming the beam. It's only like a fraction of it, 10-12% of it shoots up as the beam, and the rest comes out as gas, because when someone really observes it closely, they see that there is a diffuse matter near the pole, a little bit away from the star. Right. So let me go back. So the beam is injected relentlessly, meaning that it has to have a continuous supply of charged particles, and that is where it is suggested that the pair creation process takes place, and it takes place continuously. So it's something like this, that near the surface, it's a very strong magnetic field, and the pair creation creates the electron-positron pair, one which is selected by the type of field at the pole. It accelerates up, and the other one, the other part of the pair, actually hits down the surface, and it hits up the polar cap. So this is also has been modeled, and there are a lot of theories about it. So this is kind of what it really happens. Well, is thought to happen. And the rotation axis, it all depends on the type of the rotation, as like the angle with the rotation axis, that how far away the light cylinder is, or how close the light cylinder is. So now, to understand what the type of magnetic field is at the surface and what is the decay of the field there, so one has to go back to the neutron star structure. So a general understanding which we all know from like a lot of the talks here and in other places, that we do have something what's called the core, which we are not sure if it is a quark matter or a nuclear matter. It's an open question, but it has a density of around 10 to the power 15 grams per centimeter cube, and then we have the outer core, which is the nuclear matter, and then the thing which we are concerned with is the crustal matter, because this is the place where the conductivity of the matter, which is very essential for the magnetic field decay, is lower than what is in the core. So if you think that the core is of the nuclear matter, its conductivity shoots up. So then we are not able to hold any magnetic field there. So the magnetic field at the outer crust is actually most suitable to hold some the magnetic field. We are not sure where it is anchored in the neutron star. It's like a standard saying is that so we know that a magnetic field, if we have a very strong magnetic field at the core of a neutron star, then we will have a few problems. One of them is that since the nuclear matter is highly superconducting, then it can lead to Meissner effect, type 1 or type 2, where in a type 1 superconductor, the field lines are pushed out, and if it is type 2, then it forms bunches, but we won't have any dipolar field structure. So this is one problem, to have a body-centered dipole and also to host the magnetic field or to anchor the magnetic field within the star. So the other problem is that which comes from GR. It's not problem, it's a challenge that we cannot find a solution because the field, because the dipolar field is vectorial in nature and it doesn't allow any interior solutions for a spherically symmetric body. If it is so, as the field becomes stronger and stronger, then it deforms away from the sphericity, and Birkhoff's theorem is violated, and also we will be having a lot of problems from other aspects, like then it should give gravity waves and so on and so forth. But also the other thing is that the GR solutions, it's like someone. So then Luciano Rezzola and his groups actually found out the solution for a spherically symmetric body from GR, but he found out that it is not viable for any realistic equation of states. So we do have problems from the magnetic field in inside a star. So what are the way out is that, okay, let me tell you. So what we thought that, okay, and it has also been in the literature that a lot of people try to work out, how about hosting the magnetic field only at the crustal part. So we kind of took that approach. One can ask questions that, well, it's not the right approach. I know that it's not, but unless we find any way to anchor the magnetic field at the center of the star, this looks like a good option. Okay, then what we can come down to is the radio pulse observations. And with the recent observations, with all the fancy telescopes and good software analysis and large dedicated teams to take part in them, like the one which is in PTA, which is like doing a lot of good work. So they found some of the features, like the pulsar timing array groups throughout the world found a lot of the features which hasn't been explained in the present. So a lot of these features haven't been explained. So a few of them are like the mood changing, the nulling. The mood changing and the nulling are it's almost the same. So a pulsar, when it gives a pulse, then the shape of the pulse can change quite a bit. So this it's a kind of changing of the mode, and at some point of time it can become even zero. So that's called the nulling. And then there are the subpulse drift, means these subpulses that seem to drift away from their position and then afterwards come back to this. So these kind of things which has been observed. And also, last but not the least, are the microstructures. Like when we see a nice plot of the pulse profile, they do stack up a lot of the images, and then they do an integrated pulse profile, and this is what they call it noise, that they gets smeared out. So basically all of these things point to us saying that there is something going on at the surface where we don't know what kind of thing is going on. So it may be a change in the magnetic field or a change in the way the beams are formed. We don't know correctly, or any other effect that can affect the beams to be not consistent to what we are used to, and this lead us to actually work on the surface magnetic field of a neutron star or a pulsar. Now, when we talk about the magnetic field through the crustal matter, so our very old equation is the induction equation, which we get from the Maxwell's equations, and this second term, this second term on the right hand side is because the Hall drift, so it's like the drifting motion and it has a Hall current. But then this is effective only on the toroidal magnetic field path, so it basically moves around. So we cannot. So then this effect is not so relevant for us. So which we want to see how the magnetic field decay through the crust. So the first term is the ohmic diffusion, which is relevant for our study. Hence, this reduces to a simple form. And then one can see from a purely dipolar magnetic field with axial symmetry, we can take this vector potential and using a Stokes stream function, which we get it from the fluid dynamics. One can give a functional form of the potential, and then when you put this back into this equation, so we get a differential equation, which is a kind of a diffusion equation or kind of heat flow equation, right? So here the sigma is the conductivity and x is a fraction of r by the capital R, which is the radius, and then that was done in a flat space-time geometry. So what we also did is, like, because a neutron star surface and the crustal matter is basically at a 3 Schwarzschild radius. So 3 Schwarzschild radius means a 10 kilometer star is approximately at a 3 Schwarzschild radius, which means that the gravitational potential at the Schwarzschild radius is in infinite, but then it comes down to 3 Schwarzschild radius, it gets a 20% effect there. So it is non-negligible. The gravitational field is strong enough, so we can take it as a background Schwarzschild. The gravitational field is strong enough than the magnetic field, which means that the magnetic field is not going to affect the gravitational field, whereas the magnetic field is getting affected by the gravitational field. So then we take a background Schwarzschild for that reason. Makes life simple also, like when you work out the equations, and then after some manipulation, we find that the vector potential form in the phi direction can take this form, which is a little bit different from our flat space-time form. And from there, so this function g of RT, the functional form is just the same like the f of RT, which we had for the flat space-time. And then with that, we also find the diffusion equation, this kind. So then what we did, we have to solve in numerically. So then comes the important part, that what happens to the outer crust of the neutron star is there is a matter density which is changing very drastically. So we really don't the main challenge, well, so which means that the microphysics at each point change at each stage. So which affects the conductivity of the matter at each stage in the crustal matter density. So basically, and then the other problem comes in when we try to solve them numerically for 7 orders of magnitude, then the codes actually break up. I mean, we cannot have a standard way of the equation of state which we solve, and then we get the mass and all. So what happened is that a simple model was given by Urpin in 1979, which is like this. So one can find a relation density with the depth d. So r minus small r is the depth, and then one gives a form of the density which resembles the numerical work which has been done by Datta and Bhattacharya in 1995. So then the electrical conductivity which we can work out, so it should have 2 components. One is from the phonon scattering, and the other is from the impurity scattering. I think, yeah, no, this is fine. So this is the form for the phonon scattering, which is dependent on the on the temperature of the matter, and then when one works out the impurity scattering, which is more towards the surface of the which is more toward the outer part of the crust. So it is dependent on what is called the impurity parameter, which is given of this form. So I mean, this is like a model, and most of the people don't know what type of species are there and what should be the real value. So it is a standard practice that most of the people who did work on this field, they take a value from 0.1 to 0.001 and compare the results. Yeah, so the final form of the conductivity looks like this, and if we then we can also write the sigma in terms of the density, which looks a little bit untidy, but this is the form which we can get. Numerical results, as we say that this is a very standard practice for doing a diffusion equation. One solves the Crank-Nicholson method. For us, we tried a little bit different because we were having problems with the Crank-Nicholson method, which is we use the finite differencing method called the method of lines, which is not too far away from the Crank-Nicholson but has its own benefits. I should run a little bit quick. So we also needed to take a sample equation of state. So we took one as a Wall-Lecker model, and the other is the Birth-Johnson model 5. This is like a placeholder. It really don't have to be this, but we just took 2 and just try to see what are the effects it bring in on the final final magnetic field at the surface. So also it has been found that a neutron star, when it's born, is very hot, and then in the first 100 years, it emits a lot of neutrinos and a lot of other particles, and they take away all of the energy. and then they cool down, and they cool down to a temperature of 10 to the power 5.5 to 10 to the power 5.2 degree Kelvin, and that remains pretty constant throughout its lifetime, which is about 10 to the power 8 years. So these are the few results. We just try to see, I mean, what are the effects of the Q and T on the conductivity of matter. These are not really so. This is how the inner edge of the outer crust, and this is the surface. So this is how the conductivity changes accordingly. And then we found out how the magnetic field along the outer crust, how it changes with time. So when it is quite new, it's quite strong, and then we see a decay which is quite steadily going down, and see the curved space-time actually gives boost up the field a little bit than the flat space-time. So this is the one which is which we need to look at. This is at 100 years after its birth. So the magnetic field becomes, it decays by a very small amount till at the later stage it decays quite drastically. We have shown for both the equational states, and one is for flat and a curved space-time. So I'm not going to read out all these things, but it says that okay, here is something. So then what we did is that we said that okay, if this is the magnetic field, then if there is a radial oscillation in the field, then the core is more its incompressibility of the nuclear matter is much more than the surface, and crustal matter, what they call crust, it is not really a solid crust. I mean, it cannot be, because if you think of iron 56, then iron 56, its melting point is 1500 degree Kelvin. So, and we are talking about the surface temperature of 10 to the power 5 degree Kelvins of that order. So basically, what we think of crust should not be a really solid crust, but some kind of fluid molten iron, if it is so. So if you have any radial oscillation, then the crustal part will actually oscillate a little bit more than the core, and we can think of the radial oscillation coming from the breathing mode oscillations. Can be also obtained from GR, but the GR numbers are from, they are just a perturbative term which is on the nuclear forces. Anyway, the other thing is that the frequency of such fluctuations, they are found to be of the order of kilohertz from some of the old references where they worked out. So this is also good, because we have the subpulses and the microstructures in particular. So they all are in the kilohertz range. So here we see that what are the pulsations, how much maximum the field changes for a 2% change and the 4% change of the outer crust, a 0.2% and a 0.4%, which resembles to only a meter fluctuation and a 2 meter fluctuation in terms of the real numbers. So we did for two, and here is our final one, where we see that the fluctuations actually, we were quite thrilled to find out that the fluctuations actually go up in time. So this is what we found, that the delta B by B naught, as it grows with time, which means that which means that it is quite this thing that in observational data, it has been reported. I mean, it was reported before also, but this group formed like they conducted a study of 1198 pulsars from the 1000 pulsar array program on the Meerkat, and they found that there is actually the substructures and the subpulse drifting. They are more active in the old pulsars, means that if you take the fluctuations to be growing as they become old, then this seems to be, our approach seems to be quite a nice one, I should say. But pros and cons are that the pros is that it is able to show some direction that the fluctuations are growing. Cons is that the fluctuations are still too small, so we are trying now to better the results. A lot of things can be done to better the results, so things are in the pipeline. So we'll try to work out on them. I think I haven't shot too much in time, so a few of the selected references. And thank you for your attention. And just a note that if you want to know where this place is, the background picture is, it is taken by me in 2009 in a place called, it's a place called Drakensberg Mountains. And this is, so the real picture is this one. Thank you very much.
Thank you for a really very interesting talk. Yeah. You at the beginning mentioned that the core can be superconducting, but the core of the neutron star, but that assumes that you have a quark matter in the core. Having purely hadronic matter cannot give you a superconducting.
Why? Because you will have a 10% proton is all there. See, I mean, you really cannot have a neutron matter, just purely neutron. It has to bind, right? So it has to be, so at any given time, snapshot in time, you will have a few free protons. And if you think of the big number, 10 to the power 57 baryons, we did something long back about charged stars. So like 10 to the power 18 protons, free protons in that big number can give you a huge charge, right? So
you are definitely taking the beta equilibrium into account.
Yeah, it has to take place, right? Else you won't be able to bind them, and then it won't be stable because the neutron decay time is quick, right? So in order to make it stable, you will have to have a huge fraction of proton. Not huge, but it's still quite big number.
Any other questions or comments? None? Okay, if not, let's. Yeah. Oh, sorry. Shigari, of course, has to have a question.
Oh, he is sorry. I mean, you asked me to give a talk in 5 minutes and show a lot of pictures, but I mean, it's beyond the scope of this stuff.
So the temperature that you showed, 10 to the 5.2.
Yeah.
To 5.4. Is it really that narrow band?
It's like we haven't solved this, but we checked a lot of the works which they have done. They actually narrowed down, and it's not just only one work. It's like a whole lot of people, whole lot of groups worked them out. They are also they are model dependent, so I really cannot confirm. We took their numbers for granted, but of course, I mean, one of them is Rodrigo, then Fridolin. They did it like 12, 13 years back. I think Pons also did something like that. So we checked that a few groups actually gave these numbers. So it's like, But no, it is much more than that. What all of them say that it's not going to die. It's like change a lot. So the first stage is that it cools down quite drastically, and then it slows down, and then in this range. So it can change by like even if it changed by one factor, say 10 to the power 4, is still larger than the melting point of iron. So you still get a molten matter at the crust, outer crust.